Hi, the project of mine is application of active thermography on bundle jetting. Bundle jetting (BJ) is a powder-based additive manufacturing technique that uses bundle to create parts with wanted shape. It is mainly composed of 4 steps. First, one layer of packed powder is deposited onto the powder bed. Then, the bundle is selectively deposited onto the powder using inkjet to create desired layer geometry. Then the powder is lowered and a new layer of powder is deposited onto the powder bed. Powder is then deposited onto the layer again. These 2 processes are repeated multiple times until the wanted shape is obtained. The part formed by bundle and powder is called grain body. The grain body then undergoes curing process to increase its mechanical property so that it can be removed from the powder bed. In the end, post-processing such as sintering is applied to the grain body to remove bundle and eliminate internal voids to increase the mechanical properties of the final part. The advantage of BJ are saving material compared with conventional methods, fabricating parts with low limitation on geometry, and processing material that is hard to process for other additive manufacturing techniques such as high processing temperature, due to the separation of part forming and post-processing. Also, the BJ uses inkjet instead of laser generator, it has much higher yield than that of PBF, powder bed fusion, and the equipment cost is lower. The disadvantage of BJ is the need of post-processing, which brings shrinkage and deformation to the final part. To avoid this problem, we will need the grain body to be better characterized to obtain better final parts. There are many factors that determine the mechanical properties and dimension of the final part, such as packing density, saturation level, and the amount of defects. Packing density means the density of the powder on the powder bed. In BJ printing, packing density has to be high to ensure high mechanical property of the final part. Otherwise, the shrinkage of the final part will be high and the mechanical property of the final part will be low. Saturation level is the ratio between the volume of bundle that is deposited onto the powder and the volume of voids in the unprinted powder. Saturation level needs to be kept in a reasonable range. If it is too low, then the grain body is too weak to be removed from the powder bed. If it is too high, then the bundle will spread wider in the powder than designed, reducing the dimensional accuracy of the final part. There are 2 types of defects in BJ printed parts: porosity increase and large pores. Porosity refers to small voids that are too small to cause dimensional change, but can collectively weaken the mechanical property of the final part. In BJ, porosity is corrected with packing density of the powder. If porosity is high, then packing density is low, and vice versa. Large pores are large voids formed by air or air-abundant mixture in the grain body. They are likely to possess the curing and post-processing process and weaken the mechanical property of the final part. In order to obtain the best performance of the final part, the amount of defects has to be low. To control these factors, we would first need to measure them. Current methods rely on inspection after printing. However, packing density and saturation level are very likely to be collected with the thermal properties of the part. From the study of chain, we know that for quartz sand that is partially saturated with water, its thermal conductivity increases exponentially as saturation level increases, and also changes with porosity. It should be noted that the packing density, that the change of thermal conductivity is most sensitive at small saturation levels. Because quartz sand in chain study has similar porosity and structure with that of 3160 powder, we would anticipate a similar trend will occur on 3160 powder. Thus, thermal conductivity or thermal diffusivity should be a tool to determine the saturation level and packing density of BJ printed parts. Now, we need a method to measure thermal properties of BJ printed parts. Active thermography is a fast, non-destructive, and non-contact method that is suitable for this task. It is capable of measuring thermal properties and detecting large pores in the sample. The principle of active thermography is that the surface temperature of a sample after a short thermal pause is a function of thermal diffusivity, thermal conductivity, total thickness of the sample, and depth of large pores. The reason why large pore can be detected is that air or air bender has much lower thermal conductivity than that of green body. So the presence of large pole will generate a temperature gradient between the sun region and region with large poles. Active thermography can be used to study one stratum system and multi-stratum system. The word stratum is used to distinguish the word layer in boundary jetting. Stratum here refers to a flat plane of material with the same thermal properties. The method of analyzing the surface temperature data can be divided into characteristic time method and curve fitting method. Let's first look at one stratum system. It is the simplest active thermography system. For one stratum system item, the surface of the item is exposed to thermal pulse and the bottom is insulated. Therefore, the thickness of the region without large pole should be LR, and the region with this large pole at defect should be L. This is because large pole are considered as insulation of the sample due to their low conductivity. The characteristic time method for one stratum system used in this work is developed by Song in 2003. As shown in this PPT, it uses the peak time of the second derivative of surface temperature change in log scale to calculate thermal diffusivity, or depth of the depth of defect, and all thickness of the sample, as shown here in the equation. However, characteristic time method assumes that all energy is absorbed at the surface and the flash is instantaneous. For BD printed parts, this may be problematic for near surface features, because thermal pulse does penetrate into the powder and the flash is not instantaneous. So characteristic time method can only be used to estimate the thermal properties of the powder or grain body. The second method is curve fitting method for one stratum system. Curve fitting method uses an optimizer to find the analytical solution that has the least square error with the experimental data. This is the equation, and it was also developed by Song in 2003. Using this method, thermal diffusivity of the sample can be obtained provided that the total thickness of the stratum is known. The total thickness of the stratum is known. To find the depth of the large pores, the thermal diffusivity of the sample must be known. The benefit of this method is that analytical solution can involve factors such as flash duration, degree of penetration, and initial temperature distribution. Overall, both one stratum system methods are easy, simple to use, and does not require high computational cost. However, the two methods only provide thermal diffusivity. So one stratum method is used to determine depth of large pore of grain body in this work. For multi-stratum system, it can be divided into two conditions. Two strata system with semi-infinite thick bottom stratum, shortened as semi-infinite two-strata system, and other general conditions. Characteristic time for semi-infinite two-strata system is inspired by the work of Shepard and Beamer. The characteristic time method used the peak time and peak value of the second derivative of surface temperature change in log scale to obtain thermal diffusivity and thermal conductivity of the top stratum, provided that the thickness of the top stratum and the thermal property of the bottom stratum is known. This is a peak time, and this is a peak value. And this is a peak time. E is thermal diffusivity between the top stratum, bottom stratum, and top stratum. Although the consideration of bottom stratum improves the accuracy of the measurement, it still has the same problem as that of one stratum method. As for curve fitting method, it is inspired by the work of Song and L. Razay. The principle of their method in core are the same as that of one stratum method. The difference is the form of solution they use. Song uses numerical solution of the multi-strata system to process the experimental data, while Razay uses semi-analytical solution in Laplacian space. In my work, analytical solution is used instead. This method needs the same prerequisites as that of characteristic time method, and also provides thermal diffusivity and thermal conductivity. Due to the consideration of factors such as in-depth absorption, flash duration, and the presence of second strata or other strata, curve fitting method is more accurate than characteristic time method and can be applied to any thickness ratio or, if needed, multi-strata system. Also, Also, obtaining thermal diffusivity and thermal conductivity leads to thermal mass. Density multiplies specific heat, which is directly related with porosity. The disadvantage of this method is that it has high computational cost. Due to the accuracy and flexibility of considering different factors, curve fitting method for two-strata system is used to measure the thermal properties and sample compared with of the sample combined with characteristic time for semi-infinite two-strata system. The measurement from characteristic time method is used to provide the starting point and boundary of the optimizer in the curve fitting method. Now, we have learned what active thermography is and how does it work. But why do we need to use this method instead of other method? Because compared with other thermal measurement methods, it has 4 decisive benefits. First, active thermography can be used to measure fragile items such as grain body and monitor BJ printing process without disturbing the fabrication process due to its non-contact nature. Second, because surface temperature information can be obtained from every pixel of the IR camera, the thermal property distribution on the testing sample can also be obtained. This is the key to detect increased porosity of the powder and improve uniformity of the part. Third, because active thermography can detect large pore and porosity change, it can be used to monitor the BJ printing process and identify defects before the printing is finished. This saves time, energy, and material. What's more, the monitoring of BJ printing process can bring better understanding of defect formation, leading to improved processing methods that reduce defects in BJ printing. Fourth, once the relationship between saturation level and packing density and thermal properties are known, the saturation level and packing density can be monitored and possibly controlled during printing, leading to an increase of yield and accuracy in BJ printing. With these benefits in mind, the major objective of this study is to evaluate the possibility of applying active thermography to detect the changes in thermal property caused by factors such as packing density and saturation level, and leads to better quantity control of BJ printed parts. To do so, 4 tasks are set. The first task is to find the relationship between thermal properties and packing density of unprinted 3160 powder. This task is divided into 2 steps. The first step is to accurately measure the thermal property of 3160 powder. To do so, curve fitting method will be used to analyze the experimental data of active thermography in the experiment. Transient plane heat source method (TPS) will be used as reference of measurement from active thermography. The second step is to measure the thermal properties of 3160 powder under different packing densities. The experimental setting in this work is shown here. This picture is the figure of the experimental setting. It is composed by 1 IR camera, 1 heat source, and 1 flash chamber. This flash chamber is capable of control the humidity inside the flash chamber, and this is a schematic of the experimental equipment. A typical process is like this. First, the flash source apply a short thermal pulse onto the sample, and then the IR camera will record the surface temperature over time. And this is an example of magnitude of pulse and thermal and the surface temperature over time. This axis means the percentage of magnitude, and this axis means the percentage of temperature change over time. Now, then the experimental data is processed by curve fitting method combined with characteristic time method. The result from the characteristic time method is used to set up boundaries and starting point for the optimizer in the curve fitting method. The sample for this task is shown in the figure. Now, it is a stratum of unprinted 3160 powder placed on a supporting plate with holes covered by tapes and is placed in the flash chamber. The tape is thin, so its thermal effect can be neglected. The sample bottom is considered to be directly exposed to air, and since the air beneath the powder is much thicker than the sample, so we could say that this system is a semi-infinite two-strata system. The sample will be prepared by the BJ printer in the lab with different process parameters such as spreading speed and layer thickness to obtain thermal properties of dry powder under different packing densities. This is a preliminary measurement of active thermography using characteristic time method and curve fitting method. From the result, it can be seen that by considering penetration parameter and flash duration, the least square error drops 1 order of magnitude, and the measurement is still in the reasonable range. This means that the consideration of two factors does improve the fitting of experimental data. The principle of TPS method is that a temperature sensor with heating capacity is placed between two planes of the same material as shown in the PPT. And this is a sample of this task 2. It is dry 316L powder with a container. Now this container is loosely centered 316L powder to mimic the powder condition of 316L powder. And after the sensor hits the sample, the temperature history of the sensor will be used to obtain thermal conductivity and thermal diffusivity of the sample. This method, of course, measures the average thermal property of the sample. The second task, oh yeah, I forgot to say that the measurement from TPS will be used as a reference in this step. Now, the second task is to obtain the relationship between thermal properties and the saturation level of BG printed powder. This task is also divided into two steps. The first step is to obtain the thermal property of printed 316L powder. Wet 316L powder under different saturation level by TPS method. The second step is accurately measure thermal properties of powder using active thermography. The sample of TPS method uses in this step is shown here. Now, this sample is wetted and placed in the flash chamber with high humidity for some time to allow the capillary condition to equilibrate through the sample before measurement. The scale is used to obtain the average saturation level of the sample, and the tensiometer is used to measure the water potential in the sample. The gravity potential between top and bottom of the sample should be small relative to water potential over the range of interest. As time passes, evaporation will decrease the saturation of the sample, and TPS method will be used to measure the thermal property of the sample under different saturation levels. Thus, the relationship between saturation level and the thermal property of the wet powder is obtained. For the next step, active thermography will be applied to printed powder under different saturation levels. The sample has two types. This one is the same as the previous task, and the second sample is a stratum of printed powder resting on a thick stratum of dry powder to mimic the condition of printing during the powder bed during printing. Thus, the same two methods for active thermography will be used to measure the thermal properties of the sample. The sample will be fabricated by BJ printer in the lab under different saturation levels. The TPS measurements will be used to determine the uncertainty of active thermography measurements under different saturation levels. The third task is to monitor the formation of two types of defects of the BJ printing process. To monitor this formation, we will apply active thermography on BJ printing for every 10 to 20 layers. Due to the restriction of initial temperature distribution in depth of the two methods used in active thermography, we will need to pause the fabrication process and equilibrate the powder for some time before active thermography is applied to the powder. The fourth task is to develop a method to apply in situ monitoring of BJ printing process using active thermography. This task will first determine the error caused by initial temperature distribution in depth, and a sample will be flashed at different time intervals to determine the error caused by initial temperature distribution in depth. If the error is huge, then we will need a new method. There are two ways to do so. Curve fitting method based on analytical solution of active thermography involving initial temperature gradient in depth will be developed to obtain to accurately measure the thermal property of the sample. Second, phase domain method will be used. Phase domain method relates the phase delay of temperature profile to the thermal properties. It can be used to detect both shifts in average propensity from increased porosity as well as local defects due to large pores. The key advantage of phase domain method is that it is insensitive to the initial temperature distribution. There will be at least one paper for each of these tasks. That's all I have to say. Do you have any questions? Thank you. And this is my reference.